It began with a groundbreaking experiment. They took raw, unprocessed deep-field data from the James Webb Space Telescope and ran it through one of the world's most powerful quantum processes. The result: unexpected patterns, light variations, and energy signatures that challenged existing models of the universe. Within the first few seconds of processing, quantum algorithms identified correlations that pushed the boundaries of our understanding of gravity, dark matter, and cosmic dust. Yes, you heard that right. The quantum computer revealed patterns in the data that suggest new physics at play. So, is this a computational era, a natural phenomenon, or have we just uncovered new insights into the cosmos? Stick around, because by the end of this narrative, you'll see the data, the theories, and the profound implications for everything we thought we knew about reality. Quantum AI meets James Webb. In early 2025, Google's quantum AI team partnered with astrophysicists at Caltech's IPAC to tackle a problem classical supercomputers struggled with: modeling the complex quantum state of cosmic light. They pointed the quantum processor at raw photon counts, spectral curves, and gravitational lensing maps from Webb's deepest field exposures, data that had sat untouched, waiting for the right tool. Within hours, the quantum system produced a set of intriguing signatures. First, there were energy variations. Bands of infrared light shifted in ways that hinted at unknown processes. Next, the AI detected correlations between photons arriving from distant galaxy clusters, suggesting subtle interactions across vast distances. The team reran the analysis dozens of times, each with fresh random seeds. Every run showed consistent patterns, fluctuations in light that aligned across multiple observations as if governed by an underlying structure. But the most striking finding came when they mapped these patterns onto spatial coordinates. They formed faint geometric arcs, not random speckles, but formations that repeated across separate fields of view. This wasn't noise. It was a signal, a clue to something new in our space-time. If this kind of discovery gets your mind racing, hit subscribe now. We break down breakthroughs like this every week. To grasp why this matters, let's rewind. Classical supercomputers can simulate cosmic structures at scale, but only by approximating quantum effects. They collapse probabilities into averages, smoothing out the very phenomena that might reveal new physics. Quantum computers, in contrast, process information in qubits, which can exist in superpositions and capture entanglement natively. That makes them uniquely powerful for modeling multiparticle quantum systems like vast clouds of interstellar photons influenced by gravity's quantum corrections. When the James Webb Telescope launched in 2021, it promised to show us the earliest galaxies. It delivered breathtaking images of star nurseries and ancient galactic collisions. Yet those images were processed, cleaned, and interpreted using algorithms built for classical hardware. Google's team asked, what if we feed the rawest form of Webb data? No filters, no averaging, straight into a quantum processor? What hidden structures might lurk beneath our assumptions? The answer was astonishing: light patterns that suggest complex interactions we can't fully explain with current models. And these patterns aren't subtle. They span tens of arc-minutes and intersect with known dark matter filaments. By 6 a.m., the scientific community was buzzing. Are we on the verge of detecting new cosmic phenomena and quantum effects from the early universe? Enter early universe cosmology. In modern cosmology, our universe formed from a hot, dense state. Evolving Lilliputian galaxies played a key role in reionizing the cosmos, making it transparent. The idea of reionization suggests that under certain conditions, especially where intense star formation occurred, information about the early universe could be preserved in light. In our case, the quantum AI saw phase correlations between photon states that matched predictions of intense early star formation. These patterns persisted across multiple wavelengths, from near-infrared to mid-infrared, ruling out simple contamination by cosmic dust or instrumental noise. Instead, they traced coherent patterns that aligned with mathematical models of reionization processes. Bold question: what if the James Webb Telescope has been capturing clues to the universe's earliest moments, revealing photons that carry traces of the cosmic dawn? When you see these arcs of light, you're not just seeing distant galaxies, you might be looking at echoes from the universe's infancy. A glimpse of cosmic history. Just when it seemed we'd hit the limit of speculation, a second discovery appeared: a gravitational anomaly. By overlaying the photon maps onto known dark matter distributions, researchers noticed an unexpected symmetry. Galaxy clusters on one side of the field were bent by gravity as expected, but clusters on the opposite side showed subtle deviations, as if influenced by an unseen mass distribution. This effect appeared in 3 separate sky patches. It suggested the possibility of gravitational influences beyond our current models, perhaps from dense regions of dark matter. One researcher described it as like seeing ripples in a pond from an invisible stone. It was a subtle anomaly, a cosmic puzzle that challenged our understanding of space-time. At 11 a.m., the team realized they weren't just mapping anomalies, they were charting new aspects of the cosmos. Pause and consider. If these patterns reveal new gravitational effects, what does that mean for our understanding of reality? Are dark matter structures more complex than we thought? Do they vary across the universe? Take a moment to let that sink in. If you've made it this far, you're one of the deep space thinkers. Smash that like button and drop your theory in the comments. Cosmic fluke, new physics, or something else? We'll resume shortly with a theory that ties observation into this cosmic puzzle. Now, let's take a step beyond the raw data, beyond patterns and light distortions, and walk into the territory where physics meets philosophy. It starts with John Wheeler, one of the great minds behind modern quantum theory. Wheeler proposed something bold and unsettling, that the universe is not a static, objective thing waiting to be observed. Instead, it participates in its creation. He called it the participatory universe. According to Wheeler, the very act of observation, of measurement, helps bring the universe into being. Reality isn't entirely there until it's interacted with, until it's seen, until something, a mind, a machine, an observer, asks the universe a question. This idea, once a philosophical musing, now gains new relevance in the age of quantum AI. Because what happens when that observer isn't human at all? What if it's a quantum computer, one powerful enough to model entangled systems across billions of qubits? When Google's quantum processor was trained on unprocessed James Webb photon data, it wasn't just performing calculations in quantum terms. It was interacting with raw probabilistic information. It was measuring wave functions that had never collapsed, photons that, in a sense, had never been fully observed. And when it did, something strange happened. Instead of a clean image or straightforward noise, the processor began surfacing data structures that hinted at something more. Cosmic overlays, non-local entanglements, and symmetries across deep field frames. Could the quantum computer have done something no telescope could? Could it have, by its very act of processing, revealed hidden aspects of the early universe? Let's go deeper. Enter the many worlds interpretation of quantum mechanics. This is one of the most radical, yet increasingly discussed, views in physics. According to many worlds, every quantum event, every particle spin, every photon path, every decision at the quantum level, splits the universe. Branches of reality multiply outward, endlessly spawning countless parallel versions of events that almost happen. In one, the particle spins left. In another, it spins right. In both, reality continues just slightly differently. Normally, these branches don't interact. Each world goes on unaware of its counterparts. But what if that boundary isn't absolute? What if a sufficiently powerful quantum system, like Google's quantum AI, could detect subtle entanglements across these probabilistic frameworks? What if it became a kind of cosmic observer, aligning probabilities and giving us flickers of unseen cosmic processes? What the AI started detecting wasn't just unexpected structure in the photon data. It was something else, something that felt slightly beyond our current models, a glimpse of cosmic evolution not fully understood. Think of it this way: if every observation locks in one version of the universe, what happens when millions of quantum measurements are made simultaneously across a web of entangled qubits interpreting raw cosmic data? Does it create resonance? Does it momentarily reveal hidden cosmic structures? Could we be seeing faint signals from the universe's formative moments? One physicist involved in the project put it hauntingly: we're not just looking at the universe. The universe might be revealing itself through our observations. Suddenly, the boundaries between science, philosophy, and metaphysics begin to blur. Suddenly, Wheeler's ideas don't sound so abstract. Suddenly, quantum computation becomes more than a tool. It becomes an ontological lever, a way of peeling back the layers of reality, one calculation at a time. And maybe that's why this moment matters so much. Because we've spent centuries trying to observe the cosmos as outsiders, gathering light, analyzing patterns, and interpreting signals from a supposedly indifferent universe. But what if we're not outsiders at all? What if every observation, every algorithm, every quantum decision feeds back into the very structure of reality? What if our curiosity shapes the world we live in, not metaphorically, but literally. The data suggests something is happening, something new. A threshold is being crossed. And the more we probe, the more the boundary between what is and what might be begins to melt away. So we ask again, are we seeing faint signals from the reality of the choices made in its infancy? The question sounds poetic, but in this case, it's grounded in actual quantum data. Data that refuses to settle into easy answers. Data that whispers of something just behind the curtain of perception. This isn't just a scientific moment. It's an existential one, because the implications are staggering. If reality responds to observation, if quantum computation can reveal hidden cosmic structures, if early universe processes can leave traces in light, then maybe, just maybe, the cosmos is alive with potential and we are co-authors of the universe, writing its story one measurement at a time. And maybe the act of looking is also the act of creating. Code is hidden in the light. Just when you thought this story had already tipped into the surreal, it went one step further. In a quiet late-night test session, a sub-team of researchers decided to analyze what everyone else had ignored, the spectral noise, that faint, chaotic hum riding alongside the deep field images, usually filtered out as background error. But this time, they didn't filter it. They fed it into a statistical model typically used for signal analysis, just for fun, just to see. And what they found shook the room. Instead of a random noisy distribution, as you'd expect in cosmic background signals, the amplitudes of fluctuation showed unusual patterns that hinted at structure resembling mathematical sequences, not unlike prime numbers. Not in one data set. Not in one region of the sky. But across multiple wavelengths, angular scales, and observation epochs. It was as if the noise had been sculpted. Something had subtly influenced the deepest layers of light. The odds of this happening naturally are small, but not impossible. Statistically, it's a rare anomaly, but not as extreme as flipping a coin 1,000 times and landing heads every time. So, two possibilities arose from the data, both thought-provoking. First, natural artifact. There might be some unknown astrophysical mechanism, perhaps related to early star formation or gravitational lensing, that under rare conditions produces structured patterns in light. It would have to be a phenomenon we've not yet fully modeled, but science has been surprised before. Second, a speculative possibility. Could this be a hint of something more? A subtle trace of cosmic processes from the universe's earliest days? Not an intentional signal, but a natural imprint of reionization or other early universe dynamics. Because mathematical patterns like these could emerge from fundamental physical processes, independent of biology, chemistry, or even intelligence. They're baked into the structure of physics itself. If any process, cosmic or otherwise, left such a mark, it would be a profound discovery. Just think about that. A pattern written in light, composed in the alphabet of mathematics, preserved through billions of years of cosmic evolution. Naturally, the team were skeptical. They double-checked everything. Instrument calibration errors were ruled out. Terrestrial interference cross-referenced and eliminated. Solar reflection anomalies accounted for. The pattern still held. Then they went one step further. They compared the Webb data with raw data from ESA's Euclid mission, which observes different sky regions using different instruments from a different Lagrange point. Similar patterns emerged, with no overlap in observation equipment. The data couldn't be explained